Hello, today we're going to talk about Le Chatelier's principle. Now, this is still found within part 1 of the C2 module for AQA. And now we're going to focus on those higher tier topics of points 10 and 11 on the tick list about how changing conditions can cause the equilibrium of a reaction, of a reversible reaction, to shift, and what that means and why that happens. Now, Le Chatelier's principle is quite complex, but we can learn it in a very simple way by simply understanding the actions that will take place after you change the conditions of your reaction. But before we go on to that, let's first of all talk about reversible reactions as a short recap. So on the screen, you can see this is the example I have given you of a reversible reaction. A and B reacting to form C and D, but whilst that's happening, C and D also reacting to form A and B. Now you can see that you have two simultaneous reactions happening here. Now this sign here shows us that this is a reversible reaction, and the arrows at the top and bottom are meant to represent that if the reaction is exothermic in one direction, it is endothermic in the other. But it can also show that there are two reactions happening here. Now, when we talk about equilibrium, we talk about both of these reactions happening, A and B forming C and D, and C and D forming A and B. And in industry, it's really useful for us to manipulate the conditions of our reaction to enable us to have a really good yield, but also to ensure that our rate is still viable. So it's still quick enough that we're going to be financially viable in our reaction. So how can we do that? Well, what we do is we use Le Chatelier's principle, which is very simply, when a change is made to a system at equilibrium, the position of the equilibrium will move to counteract the change that was made. So, for example, if you were to change something, the equilibrium is going to try and shift to bring it back to that equilibrium level to get it back in balance. So let's look at the three things that we need to look at when we talk about Le Chatelier's principle. So first of all, let's look at changing the temperature. So when I change temperature, I am going to favour one of the directions in the reversible reaction. And that all depends on whether the forward or backward reactions are endo or exothermic. Now the rule here is when you increase temperature, the equilibrium will shift in the endothermic direction. And this makes sense because if I am increasing the amount of thermal energy in my reaction vessel, the equilibrium is going to shift in the direction which tries to absorb that. So it's going to shift in the way that is endothermic. So if we go back to our first reaction here at the top, if up here was your exothermic direction and the backward was endothermic, if I were to increase the temperature of this reaction, the equilibrium would shift in this backward direction or toward the left. And it would do so because that is the endothermic direction. And this means I would make more of A and B. And so I would increase my A and B. Now, if I wanted to increase my yield of C and D, I would lower that temperature because it would do the opposite. So in summary again, increasing temperature favours your endothermic direction, which means you will make more of the substances on that side of the arrow. And remember, you will need to firstly check which direction is endo and exo in your first reaction. Now, secondly, we can change pressure. And an increase in pressure will shift the equilibrium to the side with the fewest molecules or moles. Now, it's important that we note this as molecules and moles and not atoms. If I have a reaction where I've got a molecule such as glucose, which has lots of atoms within it, we're not actually looking at the individual atoms there. We're looking at how many molecules or moles of that molecule there, of that substance there is, rather than the individual atoms within it. Because actually, if I were to count the individual atoms, if you've got a balanced equation, that should be equal on either side. So an increase in pressure shifts the equilibrium to the side with the fewest molecules and moles. and that is to counteract and reduce the overall pressure. So if we look at the diagram that I have got on the screen in front of you, so on the left-hand side, you've got two lots of A plus B, and that leads to C and D. Now, when I increase pressure, the equilibrium shifts to the right, and it does so because this is the side with fewest moles. There are two lots of A and one lot of B, so that's a total of 3, and there is only one of each of C and D, and that's a total of 2. So there are fewer on this side, so therefore the equilibrium shifts to C and D. And that makes sense again, because if you are increasing pressure, the reaction is going to shift to where there are fewer molecules. Because if you're making substances where there are fewer of them, then the overall pressure of your reaction vessel will decrease. Equally, if you were to lower pressure, it would shift toward where there were more molecules or moles. Lastly, if you change the concentration in your reaction vessel, then it shifts away from the thing that you've increased the concentration of. Now, I like to think of this one as more simple than the others, but it's slightly more difficult to describe to you on screen, because when you change concentration, it doesn't actually show anything on the reaction. But if I increase concentration of one substance, so for example, imagine I increase concentration of substance B. So I'm reacting A and B together, and I add more B to my reaction vessel. What I'm going to end up doing is shifting the equilibrium away from it, okay? And that's to balance it out. If I am increasing the amount of B, then the equilibrium shifts in order to return some sort of balance to make more of C and D and restore the balance between A, B, and C and D. But really simply, if that's a little complicated to remember, you are shifting the equilibrium away from the thing you've increased concentration of. Now, the other way this gets asked in an exam is, imagine you're doing this reaction here, and as you make C and D, you remove C. So as you're making C and D, you remove C. So maybe C is a liquid and D is a gas, and you've got a pipe from your reaction vessel which just takes that liquid up as it's being made, which is obviously useful because you can then go and purify that and do what you need to do with it. If you remove C, then what you're actually doing is reducing the concentration of C over here. And again, what that will do is shift the equilibrium towards C and D, to this right-hand side, because you have a lower concentration here. So the equilibrium is going to shift to try and make more of it so that you redress that balance. So again, in summary, you've got 3 things that we might look at when we're talking about changes to equilibrium. We talk about changing temperature, we talk about changing pressure, and we talk about changing concentration. An increase in temperature shifts to the endothermic direction, a decrease to the exothermic. Increasing pressure shifts the equilibrium toward the side with the fewest molecules or moles. Decreasing pressure will shift it toward the side with more molecules or moles. And changing concentration, the equilibrium will shift away from wherever you have increased concentration or towards wherever you have decreased concentration. Now, in theory, that's all fine, but let's look at some examples of exam questions. Now, as I show you these exam questions, it is vitally important that you have a go. I will go through mark schemes with you afterwards, but you must try first, because that is the only way that you will learn to do it, is by making those initial mistakes. So let's look at the first question that we're going to do together. So this first question is about the Haber process. Now, firstly, if you're doing combined science and you look at this and you think, well, I don't need to know about the Haber process, that's absolutely fine. But you don't need to have any information about the Haber process to answer this question. So it says, in the Haber process, the reaction of nitrogen and hydrogen will produce ammonia. To produce ammonia is reversible. And on the screen there, you've got the equation. Name a natural resource from which hydrogen is produced. So something that produces hydrogen naturally. Part 2, the Haber process uses a catalyst to speed up the reaction. Explain how a catalyst speeds up reaction. Now that's 2 marks, and it's very clear what the definition is. You need to really make sure you know that definition. Part 3, What happens to the amount of ammonia produced at equilibrium if the pressure is increased? Give a reason for your answer. So we're looking at what happens to the amount of ammonia if we increase pressure. First, think about which direction the equilibrium would shift and therefore why. This is 5 marks worth of question, so you've got 5 minutes. Pause the video now and have a go. So now let's look at our answer. Well, the mark scheme, which apparently I have basically thrown over here, shows us that, first of all, for part 2, I've not included part 1, a natural resource that produces hydrogen, things like volcanoes will produce hydrogen. Now, part 2, the hard process uses a catalyst to speed up the reaction. It does this because it provides an alternative reaction pathway which has a lower activation energy. Ignore collisions because we're not talking about increasing the number of collisions, we're talking about that activation energy. On part 3, 2 marks here. The amount of ammonia will increase, and this is because equilibrium shifts to the side with fewer moles or molecules. Now, the way in which you word that really doesn't matter too much, as long as you are clear about the fact that it shifts towards that ammonia side because there are fewer molecules of ammonia there. You should be able to see that because there are 2 molecules of ammonia in the reaction here, and there are 1 plus 3, 4 over this side. So an increase in pressure will shift it to the right and therefore, or the forward direction, and therefore produce more of the ammonia. So that's one question. Now let's have a look at our second. Now this question is slightly longer. And this question says, in industry, methanol is produced by reacting carbon monoxide with hydrogen. The reaction for the equation is given. This is methanol here, and these are your 2 reactants. A pressure of 100 atmospheres is used instead of atmospheric pressure. The higher pressure gives a greater yield of methanol and an increased rate of reaction. Explain why. This is a 4-mark question, and therefore there are 2 points to it. The first thing you need to discuss is why is there a greater yield of methanol with a higher pressure? And again, you're looking at shift of equilibrium in this case. Secondly, an increased rate of reaction. Why does the rate of reaction increase when you have a higher pressure? And we're not talking about equilibrium here, we are talking about collision theory. So thinking about what you might say there. This is a 4-mark question, as I've said, so give yourself 4 to 5 minutes to answer it. Pause the video now and then come back for marking. Okay, so let's mark this video then. Mark this question then even, I should say. So let's go over to our mark scheme over here. And these are your answers. So first of all, when we're talking about yield, the equilibrium position moves to the product side. Now we can say that it shifts to the right or it shifts to the side where the methanol is. And it does so because there are fewer molecules or moles on that side. We understand that. We know that pressure will always favour the side with the lower number of molecules if you increase it. Now, in terms of rate, the reason that higher pressure gives you an increased rate of reaction is that there are more collisions per unit time. Now, remember, we can also say that more frequent collisions is absolutely fine, but really importantly here, more collisions alone is not good enough. We're not just saying there's going to be overall more collisions. Actually, if we had 2 reactions, one at a higher, one at a lower pressure, eventually they would have the same number of collisions, but it's about there being more collisions in a given amount of time. Do not accept anything about energy. We've talked about this as well. Remember, pressure is about frequency of collisions. And the reason there are more collisions, and more frequent collisions, I should say, is because there are more particles per unit volume, or you could say that there are more molecules and particles closer together. So in the amount of space they've got, they are a lot closer together. So that's your 4 marks there. Make sure that you have answered the questions in this video and that you feel confident to be able to tick these off your tick list to say that you have revised them.